Hi, I'm Gary Campbell. I'm Executive Vice President of Central Engineering for ARM. I did my undergraduate studies in electrical and electronic engineering. The reason being that I always really enjoyed playing with electronics as a teenager, and I thought it'd be a great career to go into, and that has proven to be the point. I started my career at a company called Inmos in Bristol, which was a really exciting company, famous for developing the transputer, which was one of the very early parallel processors. Then moved into ARM as a CPU designer initially, then moved into engineering management roles, and then progressed up into the role that I'm in today, leading the central engineering team at ARM, which is responsible for all of the IP development at ARM. So people can start doing development with ARM IP using models initially, where the model is an accurate representation of the IP. So it means that they can do their system development, their architecture, and also their software development using this model before the IP is available, which again gives time to market advantages. It also means that when we release the IP, we often will give partners early releases of that IP so that they can start doing early development. So they can start, if they're going to do the whole physical implementation themselves, they can do the floor planning with early releases that we give them. So when the final release of the IP becomes available, they've got a head start because they've already done the floor planning and defined their flow, and then they can just execute on the implementation, which again gives them that time to market advantage. Yeah, so the reason people come to us for IP is because IP development is very costly and complex. So we solve those problems. We provide IP that people can just pick up, which means that they can go to market faster because they can focus on the rest of their system. As well as producing IP, we also produce compute subsystems where we do that integration of IP into a compute subsystem where we've solved the integration and performance challenges, which means that there's even further acceleration of time to market. And it means that companies can focus on where they can add value. And this is really important for the semiconductor ecosystem as a whole, because there are talent challenges in the semiconductor ecosystem. And this is one of the reasons why ARM was one of the founders of the Semiconductor Education Alliance, where we are working with academia and governments to solve this talent pipeline for the industry. So at ARM we provide a breadth of IP, CPUs, GPUs, system components such as interconnect and interrupt controllers, neural processing engines, as well as all of the enabling software that goes with that. So these are all typically very complex IP, which are expensive and complex to develop. And so by providing these IPs, it means that our partners can produce systems very, very quickly using these sort of pre-configured, pre-verified components that they can just then build systems around. And we've also solved the software story for those components as well. So software engineers are involved in the development right from the start. So when we are coming up with new architecture features, say new instruction sets, the software teams at ARM are involved in helping to develop that architecture to make sure that that architecture feature can be supported in software and is also performant in software. Then when we produce the IP components, the software teams work with us on enabling performance optimizations of those features. So looking at, say, compiler optimizations for specific instruction sets as an example, taking advantage of the knowledge of the microarchitecture to get the most performant out of that system. And then when we release the IP to the market, then the ecosystem software teams are ensuring that the software required in the ecosystem to exploit and get the best performance out of those features are available. So software engineers are involved right from the very inception of new architectures, right through to when we enable those features in the ecosystem. Yeah, so the performance and the performance requirements and the power constraints are very different across different segments. So if you take a deeply embedded CPU, that maybe goes into a device that's battery powered. The performance requirements of that CPU is less than something that would go into a data center where, for example, large language model training, there is thousands and thousands and thousands of high performance CPUs and GPUs running in a very, very, very different power profile. So that means that the type of IP that is used varies quite considerably. So it really comes down to the performance and the power requirements of the segment that the IP goes into. ARM is a contributing member to the UCIe consortium, which means that we contribute to the standards that's developed under that consortium. Why it's important for ARM is it means that our IP and our systems can interwork with chiplets from other organizations. So it's very important that as an ecosystem that we work on these standards together. So RTL is still the predominant language for developing IP. HLS, or high-level synthesis, is useful for sort of replicable structures, so replicable data paths. For things that are more complex, HLS typically isn't as good. AI offers a lot of very interesting opportunities, both for RTL generation, but also the entire flow. So it's very good for automation, it's very good for removing manual tasks, it's very good for producing templates, it's good for helping to sort of triage and really accelerate verification, as well as implementation techniques like optimizing place and route. I think we're sort of still quite early in the days of exploring the capabilities of AI, but I think there's plenty more to come. Yeah, so the fast model is representative of the IP. So the fast model can be available right at the start of a development, whereas the RTL or the IP may not be available until, say, 1 year, possibly 2 years later. So it means that the system development and all of the software development can happen right early on in the development. And if you look at sort of historically, a lot of companies couldn't start producing the software for their system until they had hardware back that they could then start developing the software on. Whereas nowadays, that software can be developed in parallel with the development of the IP. So when that chip comes back, the software is ready to run. The simple answer is there isn't one size fits all. So if you look at the compute requirements to do large language model training in a data center, that's connecting tens of thousands of CPU, GPUs together, running workloads for several weeks or months. Whereas, say, edge inference requires potentially a very small power constrained single processor. So the actual, the workloads that are run are very different, which is why having different solutions is needed. So our ARM's approach to this is we can run AI anywhere. We have multiple solutions, whether it's the CPU, the GPU, the NPU, or the neural engine. And we provide the solution that means that we can provide compute wherever AI is needed. ARM provides secure solutions like TrustZone, CryptoCell, and PSA certified frameworks that establishes root of trust and secure execution environments. Through our ecosystem, from EDA companies, foundries, silicon partners, and OEM, establishing secure provisioning, integrity verification, and traceability across the system is key.